Okay, well let's move on to our second presentation. I'm very pleased to welcome, and pronounce it wrongly I'm sure, Ian Schmutte, which is my sort of German version, who's going to be presenting joint work with John Aboud, who a number of you will remember from the first workshop that we held. So, very pleased to hear you.
All right, thanks. Thanks for inviting me. It's been nice to be here and visit the Isaac Newton Institute. I've been visiting, actually sort of lurking here for about the last week or so. It's been a really fantastic visit, and I've been grateful to be here. It's been a productive and enjoyable time. So, as Chris mentioned, my name is Ian. In the United States, I pronounce it Schmutte. When I come to when I come to Europe, I just say Schmutte because it makes it easier for everybody to understand what I'm saying. So I'm from the University of Georgia, and I'm an economist by training, so just to kind of give full disclosure about sort of the perspective that I'm going to bring on these issues. So today I'm going to be presenting work that's joint with John Aboud, who I've been working with on these and related issues during my dissertation and subsequently for about the last 10 years. I'm going to be talking, the paper today is Revisiting the Economics of Privacy, Population Statistics, and Confidentiality Protection as Public Goods. I want to say from the outset, the paper is under active revision, but the version that's here will always be sort of up to date. In fact, that's what I've been working on this past week. While I've been here, some new revisions, and so some of that will show up in today's presentation. And I also want to say from the outset that sort of, as economists, economics has been accused of being sort of a hegemonic social science in the sense that we sort of like to take our tools and apply them sort of willy-nilly to all sorts of questions. And so unlike Laura's presentation, which took sort of a holistic view of privacy, we're going to look at privacy from the context of differential privacy. And what we like about differential privacy is that differential privacy allows us to think about privacy as sort of a commodity, right? Something that individuals can have utility over and that we can measure, something that people have preferences for. And so it's this ability to commoditize privacy that's very appealing. And so as economists, once we see something that looks like a nail, in this case a commodity that can be bought and sold or that people can have preferences over, we have a whole bunch of hammers that we can hit it with, and we're happy to do so. And so that's what we're going to be doing today. A bunch of disclaimers, including I've already gotten in my disclaimer for that we've been asked to include here. Okay, so the problem that John and I are interested in this paper is that data curators essentially confront a trade-off. Right, a data custodian, a statistical agency like the Census Bureau, has a sort of dual mandate, which is to, on the one hand, provide detailed and accurate statistics. So it needs to publish information that goes into the public domain that can be used by individuals and firms to, as well as policymakers, to improve decision making. At the same time, statistical agencies are responsible for protecting the privacy and confidentiality of the individuals and businesses whose information actually resides in that database. Over time, the demand on both of these dimensions has been increasing. We've already heard a bit about sort of the increasing salience of privacy concerns in the United States and elsewhere. At the same time, statistical agencies and other data providers face increasing demands for more and more frequent, more detailed, and more accurate data releases. And so statistical agency finds it under sort of pressure to improve on both dimensions. The question that we want to ask in this paper that we're trying to shed some light on is from a data provider's perspective, sort of what's the optimal trade-off between providing detailed statistical data and protecting privacy and confidentiality, given that the data have already been collected. So we're going to think about a world in which, in order to increase accuracy, you necessarily have to compromise the privacy of the underlying individuals in the data. And what the differential privacy framework gives us is a way of exactly modeling what that trade-off is and thinking about measuring it so that it can become a sort of policy-relevant parameter. So we want to think about providing policy guidance to statistical agencies and to the legislators that oversee them. Okay, so we're taking unapologetically, or maybe I'll apologize, but we're going to take an economic approach. And so we're going to sort of write down the simplest economic model that we can think of to kind of start to get a handle on this problem. And so we're thinking about, right, from an economist's perspective, this makes a lot of sense. We've got something that's sort of a finite resource. So we're going to be thinking about data that have already been collected. So we're not going to be modeling the process of going out and acquiring more data or deciding how much to spend on sort of increasing the count. We're going to assume that we've already got the decennial census, or we've already got administrative record data from some source, and now we're trying to decide exactly how we're going to publish information on the basis of that underlying private database. Okay, so that's a finite resource, and so as economists we're used to thinking about sort of we've got scarce resources and we've got competing wants, and our competing wants here are the publication of accurate statistics versus sort of the loss of privacy. That's the key trade-off that we're going to be thinking about. So going back to the theory of basic welfare economics, we know that if we can describe privacy loss and statistical accuracy as basically being things that we can measure quantitatively, then given some additional assumptions on the relationship between those variables, we know how to characterize the optimal decision, right? In other words, we know how to characterize exactly how much privacy protection the statistical agency should provide and how much data accuracy. And that should be the allocation that equates what we call the marginal rate of transformation to the willingness to pay. So this is economics jargon. And since I'm not in an economics crowd, I'll talk a little bit. The marginal rate of transformation in this context is if I've got a fixed database, the marginal rate of transformation is the rate at which you can generate increased statistical accuracy, precision of the published statistics, at the price of incurring greater privacy loss. Okay, so think about that as being sort of the cost of production. Okay, but the cost is now being measured in privacy loss. I can increase accuracy, but I have to buy it. I have to buy it with an increased level of privacy loss. Okay, so that's the marginal rate of transformation. And I want to equate that with what's called the marginal rate of substitution, or in this context we can think about it as the willingness to pay. So the marginal rate of transformation sort of describes the statistical agency's production possibilities, basically what kind of combinations of privacy and accuracy it can generate. And I want it to operate at the point, ideally, that's just equal to the willingness of individuals to pay for increased accuracy in terms of foregone privacy. So in other words, if I can go out and measure individuals' preferences, okay, and this is where a lot of assumptions are going to come into play, if it were in principle possible to measure people's preferences for statistical accuracy and for privacy loss, we're not going to assume this in the model, but let's just say for the moment that everybody has exactly the same preferences. And the willingness to pay is going to be how much a person would be willing to give up in terms of privacy loss to increase the accuracy of published statistics. Okay, and so the optimal allocation says, right, very simply, that the cost of providing increased statistical accuracy should be exactly equal to sort of the willingness to pay of the average individual in the population. In the context that we're going to consider, we're going to think about accuracy and privacy as being pure public goods. So again, in the economic setting, a public good is one that has two key characteristics. It's non-rival in consumption, which means that my consumption of it does not detract from your ability to use it. So in the context of statistics, this makes a lot of sense, right? My ability to use publications from the decennial census does not take away from some firm's ability to use the same information to decide where to locate a new business establishment. Likewise, a public good needs to be non-excludable, which means that I can't prevent someone from using the public good. So we'll concede right up front that assuming that accuracy and privacy are public goods is not sort of without some loss of generality, but we think in the context of federal statistical systems that are sort of charged with providing equal protection under the law in terms of privacy protection, which will make privacy sort of have a public good character. I have to guarantee the same baseline level of privacy protection to everyone. And the publication of statistics, at least the way that's currently practiced, those are provided sort of freely to everyone. So we think this sort of non-excludability and non-rivalry fits here. And so in that context, we'll actually find that private provision will provide suboptimally low levels of statistical accuracy. And so one of our concerns motivating the paper is that there's sort of there may be an excess emphasis on privacy protection if the sort of full benefits of having more accurate statistical information is not taken into proper account. And so hopefully part of the policy guidance would be to properly weight the benefits that come from producing more accurate statistics. Okay, so just to kind of break up the boring words on the slide part of the presentation and to kind of lodge some, right, in a picture is worth 1,000 words kind of perspective. What we're going to be looking at is a model where we've got two variables that the data custodian has to choose between, and we're trying to figure out sort of what's the optimal combination. So here on the horizontal axis we have privacy loss. So from society's perspective, that's a bad thing. So as it increases, right, things are becoming worse. And on the vertical axis is accuracy. These differential privacy mechanisms will allow us to characterize what we'll call a production possibilities frontier, which just articulates the rate at which it's possible to improve accuracy at the cost of increasing privacy loss. Right, so this thing has to be increasing because to produce more accurate information, I've got to tolerate greater privacy loss. The slope of this thing is the marginal rate of transformation, right? So at any point, that's the cost I have to incur in terms of foregone privacy to increase statistical accuracy. And so, right, from the statistical agency's perspective, this is the technological frontier. This represents sort of the set of possibilities. So if I know the level of accuracy that I want to target, then I can go figure out what level of privacy loss I want to deliver. Or if I know the level of privacy loss that I think I should be willing to tolerate, then I know the maximum accuracy that I can guarantee in published statistics. It's worth noting here that this assumes a set of things are fixed. So this is assuming sort of a fixed information budget, right? I've already collected the data. It has a given population size and some other characteristics. But it is possible in principle to increase the size of that information budget, for instance, by going out and collecting more data, in which case, right, I'm going to be able to shift the entire production possibilities frontier up, right? So for the same level of privacy loss, I could enjoy a higher level of accuracy. So again, if we were to kind of wholly model all of the decisions that are going on, one way to increase accuracy and keep privacy loss fixed would be to go out and collect more data, for instance, or to ask to publish a more limited range of data. We're going to assume that those things are fixed, and so we're going to stick with the key question of trying to pick the sort of optimal point along this production possibilities frontier. So to do that, we've got to imagine having a social welfare function. So a social welfare function, we're just going to define, again, by thinking about everybody in society has some preferences over privacy loss and accuracy. And a social planner that's sort of social welfare maximizing is just going to take the sum of all those individual utility functions. All right, so this is a utilitarian social planner. That's going to define the level of welfare that's delivered. And so this blue line here would be a level set if this thing is a quasi-linear utility function. So what we have here is the set of combinations of privacy loss and accuracy that the social planner would be indifferent between, in the sense that they all deliver the same level of welfare. And so this says quite intuitively that if I increase privacy loss, then if I'm increasing privacy loss, then welfare is going to go down unless I increase accuracy as well. So this thing has to be upward sloping. The slope of this thing is the willingness to pay, right? It's the willingness of individuals to pay for increased accuracy in terms of their foregone privacy loss. Sorry, their foregone privacy. And just like the production possibilities frontier, this thing, if we think about it, should be increasing as I move to sort of the northwest, right? So this red line is going to represent a higher level of social welfare. Okay, and so the social planner's problem is simply to maximize welfare subject to the fixed production possibilities frontier. Okay, so assume that my fixed database is going to give me a production possibilities frontier represented by this hopefully visible bright green line, right? Social welfare will not be optimized here. It's going to be optimized by moving to the point where the marginal rate of transformation is equal to the willingness to pay. Okay, so very simple optimization. This is a standard sort of social welfare model from economics going back to the 1950s. So nothing too fancy. And of course, if I do want to imagine the problem where the statistical agency can collect more or less data, then there's going to be an expansion path that relates, right, the optimal points for any given fixed information budget. So this dashed line represents sort of the set of socially optimal privacy loss accuracy combinations as I manipulate the size of the information budget. Okay, so as an overview, so what I'm going to do today is try to kind of go through various bits of the paper. So I'm going to introduce a little bit more formally our approach to modeling data release. So in other words, I'm going to be thinking about sort of differentially private query release mechanisms. So I'm going to model a data custodian that publishes data using a differentially private mechanism. In the paper, we spend a little bit of time with a model that just illustrates the inefficiency of private provision. So if I have time, I'll talk just a little bit about that model and then get into what I'm a bit more interested in, which is thinking about the selection of optimal privacy and data quality. And because our goal is to sort of begin developing a framework that can be used to provide policy guidance, we have some empirical applications. In other words, we want to show that these mechanisms are not only feasible, but that we could actually, in principle, start to think about how to measure the quantities of interest. So we don't think this is by any means sort of the bottom line in terms of answering these questions, but it's sort of a roadmap for where we might want to improve our abilities to measure all the different things that are sort of going on here. So our empirical applications are to the publication of income statistics and the publication of health statistics. And I seriously doubt I'll have time to get into the health statistics, so I've just presented slides on the income statistics. So our motivation to think about this paper, I guess I've already talked about it a little bit, so I won't spend a ton of time here. And these slides are presented in part for an economics audience, and so economists tend to be dimly at best aware that there are statistical disclosure limitation methods that actually affect the public use data that they're used to using. So oftentimes economists might be aware of sort of the presence of coarsening or top coding or something like that, but they may be less aware that there's other things going on like item suppression or suppression in tables, the fact that sometimes observations have been suppressed and then imputed with a new value. Sometimes they're not even aware of missing data imputation. They're unaware that sometimes records have been swapped to preserve privacy protection. So we're in this world where there are already a bunch of statistical disclosure limitation methods. And those statistical disclosure limitation methods have the same feature, which is that by imposing them, it limits the validity of the data in some sense. But in a way that's very, very difficult to measure and to think about. More modern methods involving input and output noise infusion, synthetic data, which I think there's going to be some discussion of on Monday, it looks like, and differential privacy allow for a more rigorous way of defining the statistical disclosure limitation or the privacy model in a way that can be accounted for sort of after the fact. In other words, the analyst can actually take the published data and account both for the data generating process as well as for the process that was used to protect confidentiality. So we're sort of motivated by this idea that data publication entails privacy loss. So there's no such thing as a free lunch. The statistical agencies in the United States at least operate under principles that say that data should be published while admitting no confidentiality of privacy, and of course that's impossible. You have to have some kind of trade-off here. So that presents this technological problem, which is that we want kind of data providers to understand the privacy costs of their current data publication paradigm. These differential privacy or other formal privacy models allow that, right? So to think about what that production possibilities frontier looks like, and know that if you want to publish unemployment statistics with a given level of accuracy, you're going to have to tolerate a certain amount of privacy loss. And then the technocratic problem, which is for policymakers, right, how much should they weigh sort of the privacy loss versus accuracy gain? In other words, how do you choose this optimal publication strategy? And so finally, kind of speaking more to the privacy literature, we think that at least in a lot of the literature that we've been looking at from the kind of differential privacy side, the public good character of data quality, we think at least in this context is really salient, but it's tended to be ignored in most literature. And we think this is an important consideration to sort of bear in mind when modeling how exactly to obtain and utilize data. Okay. There are a bunch of antecedents to this work, so we're certainly far from the first to kind of observe that there's this trade-off between data accuracy and foregone privacy. So risk utility confidentiality maps have a long history in the SDL and statistics literature. were motivated by a large and growing literature kind of thinking about differential privacy as a commodity, something that can be bought from individuals. The rights to privacy laws can be purchased from individuals that are participating in a database, and so we're going to extend a bit on that literature. We're also going to draw on practical models for differential privacy, so at least in my non-expert reading of the literature, many differentially private mechanisms don't actually seem to be particularly practical when you try to apply them to real world settings. We started out working with one mechanism that I won't mention that we ended up being completely unable to get a working algorithm of, and as far as we can tell, it is not possible to actually get it to run in a practical way. So we're working now with a multiplicative weights exponential mechanism, which does seem to be quite practical for the types of problems that we're working on. We're also related to a broad economics of privacy literature, and I want to focus in particular that we're sort of thinking about whether or not it's possible to model the preferences for privacy in the way that we have, and so there's some literature there that we're kind of running up against. And we're also related a bit to cost-benefit analysis of statistical data programs. Bruce Spencer has some really nice work trying to think about how you can measure the actual benefits of statistical data programs by measuring, say, the benefit that you get from being able to allocate the right number of representative seats to the right districts, to be able to quantify that. So we're ultimately going to run up against the challenge that we need to be able to quantify individuals' preferences for privacy as well as the benefits to society from increased statistical accuracy. These are all sort of, as far, again, as I can tell, sort of frontier questions in this literature. Okay, so any questions before I move on? Cool. Okay, so our basic setup is we're thinking about a model where we've got really two agents. We've got a data custodian that's endowed with a database that consists of a bunch of information from all of the individuals. So I got to jump around on this slide a bit. So the database consists of a bunch of data elements, HI, and those are collected from a set of individuals, from a population of individuals. So the key here is to sort of abstract away from sampling or anything like that. We're going to assume that the data come from an entire population. The custodian is going to publish information that's available to that entire population. And so everything is sort of at the population level here. So the data custodian has the database of individuals' private data. It's faces a set of queries, which are basically the set of statistics that it's supposed to publish. And it's got some data publication mechanism, right? A production function for taking the input, for taking the data in the queries and producing a set of answers. And its choice variables will be the level of privacy loss and the level of data quality, which we'll assert is going to be between 0 and 1. The individuals in the model are endowed with income, and in the example, the key example that I'll be considering, the private data is just the individual's income. So I'm assuming that the data custodian just has a database of everybody's incomes. Individuals have preferences in which they care about some statistic based on the information. They care about the quality with which it's produced, but they're also worried about their privacy loss. And in this model, things that are not these things are not subscripted by I because they're public goods. So once those levels are set by the data custodian, everybody enjoys the same quantity of privacy protection and statistical accuracy. Okay. Now, we assume that there's heterogeneity in people's preferences for statistical accuracy and for data privacy. So in other words, we're going to allow everyone to have a different taste for data quality, and we're going to allow everyone to have a different distaste for privacy protection. So this is going to allow us to have a model in which it needn't be the case that everyone cares about statistics, right? Most people probably don't. So we can have a handful of people that really care about statistical accuracy, a handful of people that have really strong privacy preferences. That's fine. We're going to be able to kind of tolerate that in the model. Okay. So now I need to talk a little bit more about the actual data publication process. Okay, and so this is all moving towards sort of thinking about these differentially private mechanisms. Okay, so the database D we're going to consider to be a collection of elements H sub I from a finite and discrete data domain. Okay, so it turns out to be problematic. This is an assumption of convenience, but it's sort of without loss of generality in the sense that any time a statistical agency is collecting data on even something like income, it's going to be rounded to some level. There's going to be a bottom feasible value, top feasible value. And so this is sort of without loss of generality. And then the database can then be represented by a histogram that has a length that's equal to the number of elements in this data domain. So in the simplest example, and the one that I'll consider, is one where there's just a histogram over the income distribution. So imagine that I've broken up the income distribution into fixed bins of size, say $2,000 bins. Every individual is going to have an income that's inside one of those bins. The labels on those bins are non-private. And then the histogram is just going to be a vector of length equal to the number of those bins, and the entry in each cell will be the number of people who had an income that fell in that bin. I'm not going to use this double bar notation too much, right? But so the one norm of this histogram is just equal to the number of records in it. Mostly I'm just going to be interested in the population size. And I'm going to be interested, for talking about differential privacy, in these sort of adjacent histograms. And so we'll define two histograms as being adjacent if they only differ in one entry. So basically the inclusion or exclusion of one individual's income in the example that I've been giving. Yeah, Laura?
Sorry. So like you consider the width of the bin to be fixed? It's exogenous? Or does it come out of the model? Because I would expect that affects privacy loss, right? So if you have a shorter bin, I know everyone that's in between 0 to 1,000 versus I know everyone that's in between 0 to 50,000.
Yeah, that's right. Yeah, so I mean, in the extreme case, right, I could have one bin and I just know that everybody has an income or something like that, right? Then there's no privacy loss, right? If I define this as there's one bin for literally every single income, then there's going to be a different level of privacy loss, and that's going to shift that sort of information budget. So I could define the data domain in either of those ways and still run a differentially private mechanism, but it's going to be relatively easy or hard to provide a given level of privacy protection depending on how I define the data domain. So you're right.
I guess I'm saying it's exogenous, so it's not. It doesn't come out of the model. Right?
No, that's right. Yeah, that's right. It's exogenous. Yeah, correct.
Maybe a useful clarification is that for differential privacy, the amount of noise that you need to add to each bin doesn't depend on the number of bins at all. But if you have fewer bins, there are going to be more people in each of those bins, and so the ratio between the amount of noise that you're adding and the count in the bit is going to change.
Okay. Yeah. Thank you. Okay. So another way to think about this is we can think about the database as being a giant contingency table. So this mechanism can also be applied to, say, more standard sort of demographic data setting where, say, I've got information on race, ethnicity, and gender. Then this data domain will be all possible combinations of values for those characteristics. So if I'm a white, non-Hispanic male, then that's going to be my entry, my value for this data. And this is going to, right, I can represent, then the histogram is just going to be a vector that has a length that's equal to the number of all the possible configurations of the data. So in this context, we're going to be interested in sort of counting queries, so I don't need to spend a lot of time here. So basically, a counting query is just going to be a vector. When I take the inner product of it with the histogram, it's going to give me the count of all of the observations in the set of histogram cells that I'm interested in. And so these counting queries are going to allow me to, say, count the full population if I want, or to, again, to go back to my demographic example, it would allow me to count the margins of the contingency table, so I could get just the total number of males, the total number of females, the total number of white, non-Hispanic males, and so on. Or in my income example, I could get all range queries, right? So I could get the count of all individuals that have incomes between some point A and some point B. All right, so these are different possibilities. In practice, we're going to work with normalized queries, so we're going to always normalize our output by the database size, in which case we're just going to be looking at the share of individuals that are in any given cell. And this just affects the way that we represent the accuracy bounds. Okay. So the query release mechanism, so what's the production technology for the data custodian? So it's a random function that takes as its inputs the histogram and a set of queries to be answered. So whatever the queries are that we want to respond to, and then it's going to give an output, which is essentially a set of answers to all of the queries. But it's going to be a randomized output. And so that's all I need to talk about here. So essentially we've got a production function where I can take any histogram, any set of queries, and it's going to give me a set of answers to those queries. Okay. So where do we get privacy loss? So we're modeling privacy loss via this concept of differential privacy, which is a property of the mechanism. So it's not a property of the database or the set of queries. So once I have a differentially private mechanism, its output will be differentially private regardless of the inputs that I give to it. And it sort of provides a measure of worst case privacy loss. So in other words, it tells me sort of what's the maximum amount of new information that can be leaked to the public through the publication of the the publication of the mechanism output. And the intuition behind what kind of guarantees privacy is the mechanism needs to behave very similarly on neighboring databases. So in other words, it needs to generate roughly the same output when it's given a database that contains my sensitive information and when it's given a database that doesn't contain my sensitive information. So the definition we're working with is epsilon differential privacy. We're not worrying about the delta. A query release mechanism is going to satisfy epsilon differential privacy if for any epsilon and for all neighboring databases, it's the case that the ratio of the probability of observing output when my confidential data are included relative to the probability of observing the same output when my data are not included is bounded above by e raised to the epsilon. So if we take the log of the left-hand side of this thing, we'll call it the privacy loss, and so this says that the privacy loss has to be less than or equal to epsilon if the mechanism is differentially private. Maybe or maybe not an easier way to think about this is that we can observe that by Bayes' theorem, right, this is the differential privacy criterion on the left-hand side. On the right-hand side is the posterior odds ratio of the probability that my sensitive data were being used, conditional on observing the output relative to the prior probability that my data were included in the mechanism. All right, so this is telling me exactly how much new information can be leaked relative to what somebody knew before and after the data were published. Okay, and again, so that's bounded above by e raised to the epsilon. So if epsilon is 0, this would be perfect privacy protection, and there would be no difference. Basically, that would be the leakage of no information. But that would also mean, because no information was leaked, that there's also going to be no statistical accuracy associated with that publication. Yeah, Laura?
Sorry. So, I guess I'm having a hard time understanding what you mean by information. And I guess in the model, it's just the amount of data that's present in the database, right? Mm-hmm. But the problem that we incur when there is, release of statistical data is inference. So given a particular piece of information, whether a particular piece of information is provided or not, you can then infer a lot of other stuff. Mm-hmm. So shouldn't there, you're not including any kind of limitations on the amount of inference that can be done based on the. I'll give you one example, right? So Christie's work on the estimation of your social security number, mm-hmm. right? So you don't need to release the social security number in order for it to be known. You can infer it if you have other stuff, which is location, date of birth, and so and so. So I don't have to release that. But if I release the other stuff, I actually allow for inference of that other stuff. So that's not included in the model, right?
Well, let me. So I'll come in a moment to kind of exactly how I'm going to be defining the accuracy of the published statistics, but I don't think that's what you're asking me about.
No, I'm just asking about, so let's call it re-identification issue, mm-hmm. right? So I can, based on specific pieces of information that are released, I can re-identify somebody, yep. which I couldn't do at all mm-hmm. if that information wasn't available in the first place. So your model looks at information in terms of what are the data points on this database that are released. But it doesn't take into account the fact that once a certain subset of data points, or let's call them vectors of specific pieces of information, allow for the inference of other stuff, that maybe it's present in the database, maybe not, but it can be inferred. So it doesn't really matter whether it's released or not.
Yeah, well, so I think that's accounted for here in the idea that you're coming to, right, after the information has been released, right, it's going to give me, I'm going to have a posterior probability on your sensitive data item, right? And before the data are published, I've got some prior belief, right? So that could be all of the information that you've acquired, right? Because you know my place of birth and all these other things that are going to tell you some information about what some of the digits of my social security number are supposed to be, for instance, right? And this is just saying that I'm going to limit the amount, right? So this, right, the prior could actually be very high, right? But there's still going to be a limit on the amount of new information that can be released relative to what you had in the prior. So I think that's how that sort of thing is addressed here. Okay, so our first model is one of suboptimality of private provision, and so I was trying to do this in one slide, but it turns out I need two. Okay, so let's think about how this model can work in a particular context. And so we're basing this on a really nice paper by Ghosh and Roth from 2011. So they consider a data custodian that, like our data custodian, has information on a fixed population of individuals and is now trying to decide how to produce an answer to a single query such that the loss from the query, right, the publication, right, the answer relative to the truth is bounded above by alpha. Okay, so that's going to be the accuracy. So they've got a mechanism, a differentially private mechanism, Laplace mechanism, that can produce statistical accuracy with level alpha by buying a fixed amount of privacy loss, epsilon, from each of a set of individuals. So once I know how high I want accuracy to be, I know how many individuals I need to get to participate in the mechanism. The model assumes that the individuals have the right to opt into or out of participating in the mechanism, and so what the provider needs to do is make payments to each of these individuals to tolerate a given amount of privacy loss. Okay, and so the kind of key result in the paper is that they can derive a minimum cost procurement auction that guarantees that they're able to hit the target level of accuracy. So in other words, given a fixed accuracy target, I know how to get the minimum cost the minimum cost mechanism, and it's essentially to buy privacy rights from the least privacy-loving members of the population first. Okay, so that's a nice result, and our extension of it is to simply say, well, in their model, they're taking alpha as being given. And so in our context, individuals in the population don't just care about their privacy loss, they might also care about the quality of the data publication. So think about this as being a database of faculty salaries or something like that. You might want to pay me to allow my data to be used in sort of a publication that talks about the distribution of faculty salaries, but I'm also going to be interested in sort of querying that database to see where I stand relative to my peers or something like that. So I've got an interest in both the data quality as well as in my own personal privacy loss. Okay, so we close the model of demand and supply for data quality by assuming that the firm is going to sell a population statistic, and we're now defining data quality as just the added 1 minus alpha. All right, so as this thing gets larger, the data quality gets better at a price per unit of quality of P sub I. And again, I and epsilon are going to both be public goods. Okay, and the key result from our extension of this is that the amount of data accuracy that's provided using the Vickery-Clark-Groves minimum cost mechanism is going to be less than the privately provided level if the firm could perfectly price discriminate. So if it actually knew the preferences for privacy of everyone. And that's going to still be less than the Pareto optimal level. And essentially what's going on here, the key intuition, is that the private producer, because it has to buy the privacy rights from the people in the database, internalizes the social cost of the privacy loss. But it doesn't internalize the full social benefit of the published data. The amount of accuracy that's going to be provided will be determined by whoever values the accuracy the most. And then everyone else is just going to free ride over the amount that that person chose to produce. So this free rider result is a standard result in sort of the economics of public goods. and it turns out to apply in this setting, again, because of the sort of asymmetry between the kind of internalization of the cost of privacy loss, but the kind of fact that there are external benefits from the purchase of data accuracy. Okay, so there are a lot more details to this model in the paper, but in the interest of getting through everything, I want to think now about sort of our attempts to characterize optimal provision. Okay, so we're going to model the optimal provision of privacy loss and data accuracy in a more general environment where we allow arbitrary queries against a confidential database, assuming the publication technology that the data custodian has access to is the multiplicative weights exponential mechanism due to one of our participants today and co-authors in the 2012 paper. And our application will be to the publication of income statistics. So basically, what are we going to do? We need to, first of all, to have a reason why individuals care about data. And so we're going to have a model of preference interdependence. So think again about the example I gave of a sort of faculty salary database. I care about that information because my preferences or my utility depends on knowing that I'm richer than most of my colleagues, or conversely, my utility suffers from finding out that I'm being paid considerably less than my colleagues. Okay, this is a model with some empirical support in behavioral economics. So we know that while the kind of classical model of utility maximizing individuals says that I should only care about my own income, it turns out that in reality most people care about their income relative to the others around them. So we're going to have a model of interdependent preferences, and we can calibrate the production possibilities frontier and the marginal rate of transformation using data from the American Community Survey. So in other words, I'm going to generate a sort of fictional population level database of incomes, and we're going to assume that that's the one that the data custodian uses to publish information. And then I'm going to calibrate the marginal rate of substitution or willingness to pay parameters using data from a federal statistical system public opinion survey. So this is a relatively new survey being conducted out of the Census Bureau Center for Survey Methodology that's trying to collect information on trust in the federal statistical system. So this has a couple of questions that we're going to try to use to proxy for individuals' privacy and accuracy preferences. And I think what it will essentially highlight is that the extent of data on privacy preferences, and especially on preferences for statistical accuracy, is pretty poor. So, full disclosure. Okay, so the data publication technology. I'm not a differential privacy guy, and I'm not an algorithm designer, so I'm not going to really pretend to be here. But just to give sort of the basic flavor of the data publication technology, essentially works as follows. So this multiplicative weights exponential mechanism operates by maintaining a synthetic version of the true data in storage, right? So to begin the algorithm, I might start, right, if the true database is the histogram of individual incomes, then I might start out with a histogram that just has a uniform distribution. And then I'm going to answer queries against that synthetic histogram. And the essential idea of this is to sort of preserve the privacy budget by by answering queries against the synthetic database as often as possible. Okay, so at each round of this mechanism, for every query, it's going to compute the score on each query as being the distance between the query evaluated on the true data and the query evaluated on the synthetic data in its current state. It's going to choose a query with a probability that's proportional to that score. So in other words, the worse that the worse the synthetic database does in answering the query and getting it close to the true answer, it's going to focus on that. The probability of selection is going to be higher. So it's going to take that query and compute an answer that is equal to the truth plus some Laplace distributed noise. And then it's going to take the underlying synthetic database and reweight its entries so that it provides a better approximation to this distorted response. It's going to do that until we've gotten to the end of the number of iterations, and then we'll publish all the query results against either the final database or the average of all the databases towards the end. So I'm going to be thinking exclusively about the context where we're just publishing the responses to all the queries that have been targeted at this mechanism, but in fact at the end of this you could also just publish the synthetic data and it would have the same differential privacy guarantee as the query responses. Okay, so there's a theorem then that we associate with this, but it really just says, this is just borrowing from the paper that introduced this method. We know that that mechanism satisfies epsilon differential privacy, and we also know that it satisfies the following accuracy guarantee: the worst case loss between any query that you ask on the data relative to the published answer is bounded above by alpha. Okay, so this gives us a worst case sort of accuracy loss. So it's going to give us this with high probability, and alpha is related to the privacy parameter which we've set according to this relationship, where k is a constant whose value we can calculate, but it's a function of the size of the data domain, the size of the number of queries, and the population count. Okay, so this is the thing that's shifting around basically the location of the production possibilities frontier. Okay, so there are a bunch of sort of boring and not that useful details on how we kind of can define this thing as a production possibilities frontier. So in economics we want to define a transformation function that basically just describes the way that we can produce different levels of privacy loss and data quality. The production possibilities frontier is that boundary, and so, but basically at the end of the day, we're just going to be saying the production possibilities frontier is just equal to 1 minus that accuracy guarantee, because we want, right, and this is just purely for our interest in defining data quality as a good rather than as a bad. But we could define the whole problem in terms of alpha, so we could have trade-offs between, right, inaccuracy and privacy loss, and everything would be exactly the same here. Okay, so this just brings us back to the beginning of the talk, right? The production possibilities under this mechanism, right, give us the production possibilities frontier we talked about before, but now with the marginal rate of transformation, right, defined as the ratio of the derivative of the transformation set with respect to epsilon and the transformation function with respect to data quality. So that gives us our marginal rate of transformation. Social planner's problem says that we're going to take the sum of the individual utilities, right? Then the social planner is going to maximize the social welfare function with respect to the parameters epsilon and I, subject to the production possibilities frontier. Okay, and so this gives us the plot that we looked at before. So a bit repetitive, I'm now realizing. Okay, so our application then to income statistics. Yeah.
So on the individual side, so you model them as discrete number individuals. So imagine that if you model that it's continuum, I guess lots of things wouldn't work, because then you can always basically violate privacy on some measure zero set of consumers.
Yeah. So I better not do that.
Possible in the discrete scenario.
So why would I want to represent this as a?
No, why in game theory set of consumers will always represent this continuum of some sort. But no, I'm just saying that it seems to be like an important feature of the model.
Yeah, so that's possible, and in fact maybe we can talk a bit afterwards, because there is an aspect of when we go through this model on the suboptimality of private provision, we do end up moving into a setting where we think about a continuum of agents, and so it's possible that we're
because always violate privacy of zero measure set of consumers, and you would have the same social welfare.
Yeah, so then we need to become probably in that context. Then we need to refine the definition of privacy loss to sort of.
If you have some queries that are discontinuous, especially on that measure zero set, that would improve the accuracy.
Okay.
Physical accuracy.
I mean, I'll confess that standing here right now is the first time I've given much thought to this issue, because we're sort of used to, I mean, it's not abnormal in the setting that we're considering to think about everything in sight as being a sort of discrete population, but I can imagine scenarios where it would be relevant to think about this as a continuum, but I won't be able to say anything any more intelligent about it than. So basically for this application we need to specify the functional form for preference. So we assume that the custodian now is publishing data on income. Okay, and so now individuals' preferences are defined by an indirect utility function that depends on the prices of a bunch of private goods that we're now no longer concerned about, the individual's income, and then the two parts that we are concerned about. So it depends on the individual's disutility or distaste from privacy loss, which depends on the level of privacy loss that's incurred, and the marginal disutility is affected by the individual's relative position in the income distribution. So in other words, the richer I am relative to the population, the more I might suffer, or the greater my marginal disutility from privacy loss. Likewise, and in parallel, my valuation of data accuracy, because I care about knowing how rich I am relative to the population, my marginal utility from information quality is also a function of my relative income. Okay, so the special case and the kind of model motivating this specification is this model initiated by George Akerlof, thinking about relative income interdependent preferences. So there's rather large literature in economics now thinking about when there are relative income concerns, how that might affect public policy as it regards transfer or tax programs. Those models always implicitly assume that, right, there's no privacy loss and that the information quality is perfect. But of course we know that people have to get their information on the distribution of incomes from somewhere, and maybe they can just infer it from looking around, but maybe not. Okay, so we're trying to sort of generalize on that basic model. Okay. Model also has the nice feature that if I look at the solution to the social planner's problem, I need, right, the marginal rate of transformation, that's the cost of increasing accuracy and foregone privacy, has to be equal to the willingness to pay. The willingness to pay is the partial derivative of the social welfare function with respect to privacy loss divided by the partial derivative of the social welfare function with respect to data accuracy. And that turns out to give us the nice functional form, right? So on the left-hand side, we have the marginal rate of transformation that we got from assuming the multiplicative weights exponential mechanism. And on the right-hand side, we have something that depends on the mean, the first and second moments of the joint distribution of privacy preferences and income. And so essentially we're going to claim to be able to measure the willingness to pay by looking for statistics that are informative about these covariances in particular. How do people's self-reported preferences for privacy and accuracy covary with their income? Okay, full solutions come from there. So what's our empirical analysis look like? So we need to measure this willingness to pay. And to do that, we use 4 variables from this ongoing Center for Survey Methodology, Federal Statistical System Public Opinion Survey, or it's the Trust in Federal Statistical System Survey. Okay, so we've got 4 variables. So they have these unhelpful labels. FS11, which we use as a proxy for latent preferences for privacy, says that people can trust federal statistical agencies to keep information about them confidential. FS14, which is another proxy for latent preferences for privacy, as we regard it, would you say that federal statistical agencies often invade people's privacy or generally respect people's privacy? Our measure that's a proxy for latent preferences for accuracy asks individuals to report on a 5-value Likert scale. Policymakers need federal statistics to make good decisions about things like federal funding. Okay, so we're going to regard each of these variables as being moved around by an underlying latent variable that is the preference for privacy or the preference for accuracy, whilst fully acknowledging that these questions might not be the most ideal proxies for those things in the world. They're the best that we could come up with. All right. We've got family income that's reported in 5 categories. Okay. So using those Likert scaled variables, we compute polychoric correlations. So we get a correlation between our measure of preferences for accuracy and income of 0.08, correlation, and 2 different measures of the correlation between preferences for privacy loss and income, 0.08 and 0.04. a few distributional assumptions later, we're able to substitute these polychoric correlations in and calculate a willingness to pay of 1.04. So this says that the social planner should be willing to forego 1.04 units of data quality for a unit decrease in privacy loss. All right, so this is just measuring the willingness of the social planner to pay for statistical accuracy. So we calibrate the data publication technology assuming we've got a population that has data from all individuals in the United States who report an income, so 197 million. We disaggregate the levels of income, again, sort of exogenously, into 797 evenly spaced bins. I'm told by our RA that that was the number that we came up with the rule that we gave him. And we assume the publication of all range queries. So all queries of the form, how many people's incomes, or what fraction of the population has an income between bin A and bin B, of which there are 318,000 such queries. Okay, so when we do that, this is the solution that we come up with, and so we find that the optimal data accuracy would be 0.086. The optimal privacy loss is at 0.04. So what we're interested in part, is thinking about sort of a counterfactual. So we could imagine, let's say that because of political pressure, the statistical agency overweights privacy relative to statistical accuracy. So we can imagine the costs associated with decreasing the level of privacy loss by 50% to 0.02. In that case, if we stay on the production possibilities frontier, we assume that the custodian still does its job properly, then that's going to decrease the level of data quality. And we can actually use our social welfare function. Like if we take the model really, really seriously, then the welfare loss would be equivalent to a 1.3% increase in income. In other words, it would be equivalent, so the welfare loss for everybody would be equivalent to losing 1.3% of income. So the compensating variation, how much I'd have to compensate people to tolerate living in a world where there's increased privacy loss, would be 1.3% of gross national income. This is the population, so it's 1.3% of GDP. Of course, this is all completely made up numbers, so that sounds like a large, a large result, but of course it's nearly meaningless. I suppose I shouldn't say that in my own talk. All right, so the other nice feature is we're actually able to simulate the publication of queries against this database. And so we look at the worst case accuracy across 30 separate runs of the multiplicative weights exponential mechanism at this optimal choice. And we find that the worst case accuracy across all the queries is on the order of about 1 in 1,000, which is very good in contrast to the guaranteed level of accuracy of alpha of about 0.14. Just kind of thinking about this in terms of scale, if you took the population and divided it sort of uniformly across the 800 bins in this histogram, right, if they were uniformly distributed, you'd have about 1 in 1,000 in every cell. So getting counts that have a guarantee with this level means there's a considerable amount of noise. But in practice, evaluated at the optimum, we actually get pretty precise responses to the queries in the worst case scenario. Okay, so just to conclude the talk, so we've talked a little bit about disclosure limitation as a kind of technology, thinking about the technological frontier. To figure out the optimal level of accuracy versus privacy loss, we need both to understand that technology, but also to be able to measure the sort of social preferences for both privacy and for accuracy. This is a public policy problem that I think the existence of this workshop and others like it suggests is important and salient, but this particular aspect of the public policy problem is largely unanswered. So we need better data. We need better data in particular on the extent to which people value privacy and privacy loss, and more information on the social benefits of data publication, whether those be individual preferences for statistical accuracy or the value that people are able to obtain from the fact that having a statistical infrastructure allows for a more robust economy. We also need more model improvements, and here I've disclosed the model that we were looking at before. So we need to be able to measure this production possibilities frontier in real-world cases. better, more accurate models of the demand for privacy and for accuracy, and we think that in general we need more economists to be working on these types of problems. And with that, I'll give, wait, is that it? No, no email address. All right, well yeah, I'm out of time. All right, thank you.
Thanks very much, Ian. I think we've got time for one or two questions. Yeah, Joe.
I have a question about your loss functions.
Okay.
You took a fixed database. Now, what about, in terms of privacy loss, what about the potential effect on the willingness of people to respond to the next census survey? It seemed to me that would play a bit of a role in both accuracy and in the privacy loss.
Yes, dynamics.
In other words, if there was a breach of privacy, for example, some information about one of our two presidential candidates leaked out,
Yeah.
that would be
Yeah.
that would be a tremendous impact on next month's CPS response rate.
Mm-hmm.
So I'm wondering whether that type of what's going to happen in next census, next census survey should be put into the model.
Yeah, so I suppose I would give kind of two reactions to that. I mean, one is clearly we're thinking about this as a fully static model, and so we're not sort of thinking about sort of the dynamic dependence on individual sort of willingness to participate on what they've learned about disclosures in the past. But that kind of dynamic model would be interesting, and my intuition would be that if people actually understood, if we're using a differentially private mechanism and people understood that fact, then in some sense they should understand the privacy guarantee, and unless their preferences themselves change, it shouldn't really affect their willingness or not to respond, because the amount of new information that's going to be disclosed shouldn't change. That's just sort of my knee-jerk reaction to that. The second thing is, at least looking in this federal statistical system survey of attitudes on trust in the federal statistical system, they're surprisingly, they change a bit over time, but they're not as sensitive to the kinds of disclosures like the Snowden disclosure, the kinds of disclosures you were talking about, as I might have thought. In other words, at least the measures that we're looking at, which I've already given some caveats about, seem to be relatively stable over time. But I do think that, you know, to take this kind of model forward and more seriously, we would need to think about sort of the interdependent, right, the kind of dynamic consistency of people's preferences over time and their willingness to respond. I think that's true. Yeah.
So, I could be mistaken, but I think, so with your kind of like loss functions, you're basically saying your aversion to kind of privacy loss increases with wealth, right? I think.
Mm-hmm.
But at the same time, like the distribution of wealth isn't even, right? So like if you're in the kind of the higher end bins, it's going to be fewer people. So any sort of query where you're kind of involved or revealed has a higher kind of cost for the differential privacy. So in some sense, it's counting kind of wealthier people more than less wealthy people, right? So for your social maximization, I think it might be, I mean, your welfare, it's kind of counting rich people more than less rich people in some sense, right? So I think if you maybe are weighting the preferences by kind of how much they matter in terms of the differential privacy, then maybe you get a kind of more optimal output or something, and less the kind of willingness to pay cancels real.
So let me just say the following back to you, and then see if I've understood your.
Yeah, sorry. Is it?
Yeah, no, it's all right. So it is true that the marginal disutility from, say, privacy loss, the way that we've written it down, is a function of your income relative to the mean. So that's the mean relative to, and we're expressing incomes here sort of in logs. So we're thinking about sort of the distribution of logarithmic income, which is going to still be kind of fat-tailed, but it's not going to be quite as skewed as the distribution of income in levels. And so in that sense, we're going to be there are going to be some people who have incomes below the mean, or log incomes below the mean, and incomes above the mean. And so depending on the way kind of preferences for data accuracy are distributed, those two things might cancel out. So in other words, I think in our model, we're kind of overweighting people that are far away from, right? If you have income that's exactly at the mean, then that term cancels out, and we're not including your weight at all, right? And then individuals that have incomes far away from the mean, either positive or negative, right? Again, assuming they've got the same preferences, they're going to cancel each other out. So, but maybe
One final question, then I think we ought to.
I was just wondering, is there evidence of that sort of utility for people? So some people with very high salaries, sometimes they're public, like, I don't know, like public people. And I might think, I don't think that my concern for privacy depends on my income personally. I feel like if I agree that it's a public good and it's important to do a census and whatever, I feel like I don't know, maybe I'm compassionate to others whose income might be more private than mine, and I wouldn't really change my feeling about privacy depending on my income. So I'm just wondering, so I guess it's a model, but is there evidence in theory, in practice?
I mean, there's evidence out of the CPS, if you look at the current population survey, if you look at kind of non-response and try to ask the question and survey non-response with respect to income, is that ignorable, even conditional on a bunch of stuff that you can observe? It turns out that the answer is no. So people who have particularly disclosive levels of income tend to be particularly sensitive to that question and will be more likely to not answer it. So yeah, there is some evidence that people have these privacy concerns that are a function.
Or the extremes, perhaps.
Yeah, I mean, yeah. So that's a function of their position. Again, you could think about it as being absolute or relative to the mean, but either way, kind of extreme values seem to be too sensitive.
Okay, well, I think perhaps we should continue that conversation over lunch. So thank you once more.
All right, thank you.